Okay, chapter 25 is about capacitance. Capacitance. So we simply finish the previous four chapter. I think we come to a point that it will become less difficult maybe. Yeah, because in this chapter we will maybe use some Gauss law to derive some equation for the capacitor and resistor in this chapter and the next chapter. So we have a, a, a slightly relaxed moment, and then later on we will learn the magnetic field, and I think it will be more difficult than the electric field because the yeah, for the magnetic field, you know that you need to use the cross product or the right hand rule. You need to design the uh, the B field somehow using the right hand rule, and then you will be confused. But so far, it is a little bit relaxed because you just use some previous knowledge and then you apply it here. So in this chapter, we'll learn what is actually a capacitance. Yeah, it looks stupid, but because you have already learned circuit analysis in the previous semester, but actually we um, we 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 try to analysis a capacitor in a physics point of view. Physics point of view, what is actually a capacitance, and what is the relationship between the geometric structure and the capacitance itself. We'll try to derive some formula about that. Yeah, we'll try to calculate the capacitance, capacitor in parallel and series, and I suppose of you should know that, and energy stored in an electric field, and capacitor with dielectric, and dielectric with Gauss law. It may be a bit more difficult, but actually it should be fine. So here, a capacitor consists of two isolated conductors with charge plus Q and negative Q. Its capacitance is C is defined from Q equals to CV. Q equals to CV. So this is a very important equation for the capacitance. Actually, I also use it nowadays for my research. So it's very important, especially if you try to do some IC design like the ADC or analog AI. So we frequently use this fundamental equation. So actually, V is the voltage difference between the plates. So so this is the voltage difference. And the Q is the charges stored at both plates. One is positive Q and another one is negative Q. So this ratio Q over V is what we call the capacitance. We usually denote it as capital C, which is a capacitance. So here we can see that the top plate has a positive charge and the bottom plate has a negative charge. So the electric field line you can see in between these two plates will be somehow uniform, especially close to the inside. If it's close to the edge, it will be slightly smaller because in chapter 22, 23, we try to calculate the E field between a infinite large or the electric field generated by an infinite large charge plate, which will be uniform. But here, this capacitance is finitely large. So it is not actually uniform. So we can only consider the inside part. This part is uniform. Then this part is a little bit weaker. And for the outside, we have something called the fringe E field, the fringe E field. So somehow like this, and like this, and this. So here we consider to charge a capacitor. When a circuit with a battery and open circuit and uncharged capacitor is complete by closing the switch, conducting electron shift, leaving the capacitor plate with opposite charge. So we can have a battery, and then we have a switch, and then the parallel plate. So it is not in circuit symbol, we can draw a battery like this, one long and one short line. So this one is positive, this is negative to stand for a battery, and this is a switch. If this is like this is open, and you can close the switch so that you connect both ends together, and then there can be some current going through this path. And if it is open, there shouldn't be any current going through, ideally. So if you try to close this switch, and then there will be some electron going this way, and then some electron will try to go like this. So because this is negative charge, there will be electron going this way. So the electron will store at the right plate, and the electron will try to leave it. So that you will feel that there are positive charge on the left plate, and there will be negative charge on the right plate. So this is a capacitor. This is capacitor. The charge can't go through this gap because we will consider it's an isolator. So you can only observe that the charge go away, and then the electron goes away from the left plate, and then the electron go into the right plate, so that it stores some opposite side charge between these two plates. And if this is a DC battery, then it will go to a steady state after some time constant, which is nothing but you know how to derive it after you have run the circuit analysis. So we try to calculate the capacitance, using the Gauss law. So to relate the electric field between the plate of a capacitor to the charge Q on either plate, we shall use Gauss law. So the familiar equation. So we just purely assume that there are uniform E field between the two parallel plates, and there are no E field outside. It's just an assumption. It's not actually the truth, but after we make this assumption, we can make the equation easier to simplify. And of course, there will be some error between the practical case and the derived formula, but it can at least provide a close solution to this one. If you really need to consider a very accurate value, then you may need to use some computer-aided software to really calculate the E field. Suppose it is not a uniform E field, then you need to use some numerical method to calculate the answer. But now, if we just use the hand calculation, we just make this question simple enough, but the error is not quite large, so it will be fine. So from the previous chapter, we know that the voltage difference is the negative of this line integral. And we can rewrite this one like this. The voltage difference, which is usually defined as a positive value, and we just integrate the E times dx. So we just we already consider the dot product already, and then the lower bound is the negative plate, and the upper bound is the positive plate. So we just consider a path in green color like this. So this is the negative plate, and this is the positive plate. So we consider ds from here, from the bottom plate to the top plate. ds, so ds would be pointing to upward. Yeah. Okay. So next, for the Gauss law, so because we already consider this is uniform, so the integration of E dot dA is nothing but EA, and yeah, and for this part, because this is conductor for the top edge, there will be no E dot dA contribution, and for the left and right, there will also 0. So the only one edge to contribute the integration of E dot dA is the bottom side. So it is EA times epsilon naught to be Q. EA times epsilon naught to be Q. And this is positive Q, this is negative Q, and we assume this Gauss surface is like this one. So the enclosed Q is Q, is small q. So we have V equals to this integration, and E is also uniform for this path. So we can just factor E out, and then we just integrate ds from the negative plate to the positive plate. So the distance between them is small d. So this integration is nothing but small d. So we have come to a similar simple equation. V equals E times d, which is supposed you should have learned it in high school. So for uniform E field, you can have E times d. E times the distance will be the electric potential difference. So suppose we have Q equals CV for the definition of a capacitor. So we just substitute CV to here, So we have CV, and then for E we have V over D. So we have V over D and CV from here and here. And finally, we can cancel V on both sides. And finally, C is nothing but epsilon naught A over D. So this is the capacitance of a parallel plate capacitor. And it tells you that epsilon naught is a constant 8.85 times 10 to minus 12. And the area, A is area of this plate. So if you want a capacitor to be larger than then the area should also be larger. And the D is the distance between the two parallel plates. So if you want a larger capacitance, then you need to make the distance between the two plates closer, so that their capacitance will be larger. But actually, there will be some force attracting them, so you need some structure to just hold them apart. Otherwise, they will just touch each other, and then the capacitor will break, and it will be somehow like a short circuit. So this is another case. It is a cylindrical capacitor. Cylindrical capacitor. 圆柱形的电容，圆柱形的电容。So so here you connect the inner part by the positive, and the outer part by the negative. So it's somehow like this. But here is just show the cross section of this cylindrical. So here in cross section, a cylindrical capacitor of length L formed by two coaxial cylindrical. 同轴啊，同轴，这个是同轴的意思，就是它们是同一个圆心的，同轴的 coaxial cylinder of radii A and B. So this is A and this is B. This is B. So we assume that L is much larger than B, which is maybe 100 times or more, but it depends. In engineering sense, much larger can means any number. Can means any number. It doesn't really tell you how large it should be, but it depends on the area you consider, because when you use this stuff, it somehow like take the limit, and then it's somehow like B over L is a very small number. If you just accept maybe 5%, then this one may be also 5% or a similar number. Yeah. So now we negate the fringe of the electric field, because the height here is capital M. The height here is capital M. So there will also be fringe outside. There will also be fringe outside. So in between there will be something like this. There are generally uniform, close to the inside. But if it's near the outside, then it will be somehow like this. The E field will somehow like this. But here we also assume that we just ignore this fringe effect. Only consider all the E field inside this cylindrical. The cylindrical structure is uniform, and actually you can assume that all of them are radial direction from the center to the edge. All the E field are somehow like this, because this is positive, this is negative. So, and because it is a perfect circle, then you can consider the symmetric. So we also want to the radial direction. So here you can see that all the E field are in the radial direction. and each place contains a charge magnitude, small q. And similarly, we have a Gauss surface here. This is the Gauss surface. And of course, it will have a top and bottom, but actually all the E field will be parallel to it, so it contributes nothing for the top surface and bottom surface. The only contribute part is the side. Somehow, so we consider a Gaussian surface like this. So the bottom and top will contribute nothing. So all the E dot dA are contributed by the side surface. So so according to Gauss law, Q will be epsilon naught times E times A. A is the area, surface area. And it would be similar to be, it will be, yeah, it will be somehow like this. 2 pi r. 2 pi r is the circumference of a circle, and then times the L, which is the height of the. So consider the surface area of this. You can just cut it and then just flatten it. So when you just cut it, you just cut it like this, then you will have a rectangle. So this side will be 2 pi r. And then the height will be nothing but L. So the surface area will be 2 pi r L. And we consider the V is integration dEs from positive plate to from negative plate to positive plate. So negative plate is here and positive plate is here. So you integrate from this side to that side. And yeah, so we can see that E is Q over 2 pi epsilon naught L R. So we have Q. So, so from this one, we have E equals Q over 2 pi epsilon naught L R. Yeah, we have L R 2 pi epsilon naught. So we have 2 pi epsilon naught L R Q. And actually ds is negative dr. ds is negative dr because ds is from the outside to this side, but actually r is in the reverse direction. So when we consider ds, it will be dr with a negative sign, with a minus sign. And so we actually integrate for the r variable. So r should be kept inside and the other ones are constant. So we can just factor them out when we just integrate 1 over r dr, which is nothing but ln, and ln a minus ln b will be ln a over b, and then we also have a minus sign here, so it will be ln b minus ln a. So ln b over ln a is nothing but ln b over a. I suppose you have learned it in high school. So this one is yes, like this. So it's nothing special. So finally, using C equals Q over V, C equals Q over V. Yeah. So we just divide V on both sides, and then we just put this part to the left side. So we'll have C equals to 2 pi epsilon naught L over ln B over A. Oh, yeah. So this is the capacitance for a cylindrical capacitor. So you can consider if you need a larger capacitance, then you need to increase the length of the capacitor, or you need to minimize this term, which means that the two cohesion radii should be close to each other. Because B is always larger than A. But if B is equal to A, which means that B over A will be close to 1 and ln A will be close to 0. So it will become very large, but yeah. So but actually this will be more difficult to really fabricate this kind of capacitor, because you need to make the two radii to be very close to each other, but they are actually different. And you also need to make sure the two parts don't touch each other. So yeah, there are some other capacitor called spherical capacitor. I don't actually derive it here, but actually this is not difficult. And yeah, actually, although this one looks very similar to that one, but this one is actually different. This is two sphere. That one is, because it is only a cross section. This is only a cross section. So they have the same cross section. Doesn't mean that the original structure are the same. This one is cylindrical capacitor. This one, it has two sphere, two ball. One larger shell and then one inner ball inside. So actually you can also use the Gauss law to derive this one. It's not so difficult. Maybe I will try to ask you to derive it in midterm exam or a final exam, maybe, but not necessary. But actually, it's not really difficult. I think I already asked the student to derive it in last year midterm exam. Actually, it's not so difficult, in my opinion. So this is the equation for a spherical capacitance. So it is K times AB over B minus A. Similarly, if you just make A and B close to each other, then this capacitance will be large. And there is a special case for these spherical capacitors, which means that we make B to be infinitely large. which means that we can just remove the outer shell, and then we make A to be capital R, which means that we only have a ball inside, and then it can be regarded as a capacitor. And the capacitance is nothing but 4 pi epsilon naught times R, because you can just make B tends to infinity here, and then we can just divide B and divide B. So this is 1, so this is also 1, and this will be tends to 0. So for the denominator, it is nothing but 1, and A is R. So we can simply derive 4 pi epsilon R to be this case. Okay, yeah. So let's just finish this checkpoint quickly. So for capacitance charged by the same battery, does the charge stored by the capacitance increase, decrease, or remain the same in the following situation? The plate separation of a parallel plate capacitor is increased. So this C will become smaller, and this is true for any structure. If you just make the separation to be larger, then the capacitor will be smaller. And the radius of the inner cylindrical of a cylindrical capacitor is increased, then the C will become larger, which means that it will be closer to the outer cylinder. And for C, the radius of the outer spherical shell of a spherical capacitor is increased, then the C will become smaller, because for the outer shell to be larger, then it will be farther away from the inner shell. So it is very easy.